Sometimes we take things for granted, from our ability to walk to the light that illuminates the world around us. For example, every day we walk beneath the sky, but how many people have wondered, really wondered, why is it blue? Or why does the sky begin to turn a radiant red when the sun sets? This video today will hopefully be able to answer these two questions.
To begin, we need to address the very question of light. What is it? And where does it come from? Light can be defined as electromagnetic radiation that is visible to the human eye. We will learn all about magnetism, electricity, and the relationships between them in class, which can be described by Maxwell's equations. So we will not go into great detail about that here. But the important thing to take away from this is that electromagnetic radiation has wave-like qualities. It can be quantified by characteristics such as wavelength, intensity, propagation direction, frequency, and polarization. Furthermore, in a vacuum, light, like all types of electromagnetic radiation, always has a speed of 3 × 10⁸ meters per second, which is one of the fundamental constants of nature and is of great importance to our task.
Since the speed of light is constant, when frequency varies, wavelength must adjust itself as well according to the fact that speed is proportional to frequency and wavelength. In fact, visible light encompasses just a small segment on the electromagnetic spectrum, which is the range of all possible frequencies of electromagnetic radiation. Within the spectrum of visible light itself, there are subsets of different types of visible light, in other words, colors. We see visible light as a white light, but it is in fact due to the fact that there is an aggregation of all the different colors of light. As seen from this diagram, red light has the lowest frequency and thus the longest wavelength at about 620 to 750 nanometers, while blue or violet light has the highest frequency and the shortest wavelength at around 400 nanometers. The fact that visible light has a spectrum of colors is no doubt important in explaining why the sky is blue, but it's not sufficient, for we need to consult the properties of the atmosphere.
The atmosphere is a mixture of gas molecules and other particles such as dust, pollen, soot, and salt surrounding the surface of the Earth. It is held in place by gravity and is composed of 78% nitrogen, 21% oxygen, and 1% argon, carbon dioxide, and other miscellaneous particles. These particles, often being no more than a few molecules large, have diameters ranging from generally 5 nanometers to 20 nanometers long. In fact, it is this relationship between the small size of the particles and the wave properties of light that cause the sky to become blue. As explained on the website Science Made Simple, light will travel in a straight line until it hits something. The result of this interaction is dependent on the size of the object it hits, as well as the wavelength of the light.
For example, when light hits a large smooth surface, all the light is reflected back at the same angle of incidence. The light looks white because all the colors of light have been reflected at the same angle. Diffuse reflection is when the light is bounced off in all directions due to a large, uneven, and asymmetrical surface. However, when light hits a very small particle, such as a gas particle, much smaller in diameter than the wavelength of light, a very different interaction occurs. When the light contacts a small individual particle, some of the light is absorbed, and then it's radiated in all directions. This is called scattering, specifically Rayleigh scattering. The color that is absorbed is the same as the color that is radiated. Rayleigh scattering can be described by several complicated mathematical relationships, but we will also distill the essence of these equations into a couple of key concepts.
One is that shorter wavelengths are better absorbed and scattered by the particles. As a result, blue light, which is one of the shortest wavelengths on the visible light spectrum, is more often absorbed than other colors and radiated omnidirectionally. This is thus responsible for the blue color of the sky. When the human eye looks at areas of the sky other than the sun, it receives many of the rays resulting from scattering. The resulting color, which is usually a pale blue, is actually an aggregation of all the colored light rays that have been scattered, but these mainly consist of blue and green. On the other hand, when the eye looks directly at the sun, it sees more of the longer wavelengths, like yellow and red, that have not been scattered away. Thus, this gives the sun a slightly yellowish tone. However, one may still inquire as to why are shorter wavelengths preferentially scattered.
The answer to this question has to do with the sizes of the particles and the wavelengths. In the case of Rayleigh scattering, the particles are still very small in comparison to the wavelengths, but blue light is closer in size to them than red light. A particle will absorb and scatter light that has a wavelength most similar to it in size. As a result, the longer wavelengths are the ones that pass straight through the atmosphere. That being said, have you ever noticed that the entire sky isn't exactly the same shade of blue? That maybe the bright blue becomes a little paler near the horizon?
This is simply because the light of the horizon is passing through more of the atmosphere. Rayleigh scattering increases, and more blue light is scattered away from the observer and their line of vision. However, another effect also comes into play here. A different type of scattering effect, Mie scattering. Mie scattering is different from Rayleigh scattering because it is wavelength independent, and it scatters all colors of light in the forward direction. It is the result of large water droplets and aerosols, and this is in fact the reason why clouds and fog appear to be white or gray in color. Therefore, when both Mie scattering and Rayleigh scattering occur, the sky appears lighter blue at the horizon.
Then you may ask, why does the horizon change from light blue to bright red during a sunset? As the sun sinks in the sky in the late afternoon and approaches the horizon, the light source itself is moving towards the horizon. Therefore, there are more light rays traveling through the atmosphere near the horizon at a smaller angle to the Earth's surface. In addition, the light travels further through a greater expanse of atmosphere. As a result, more blue light is scattered and longer red wavelengths pass straight through due to the wavelength dependence of Rayleigh scattering. In order to see the direct rays passing straight through the atmosphere, you need to look directly at the sun. Therefore, when the sun is at the horizon, you see the direct red light and the sky appears red in color. If Rayleigh scattering were the only phenomenon occurring during the sunset, we would never get the stunning arrays of colors across the sky that we so admire. Instead, at sunset, only the horizon would become a slightly reddish hue while the rest of the sky remained blue.
To resolve this, we need to turn to Mie scattering again. In our discussion with Professor Brown, we determined that when looking through the horizon, we look through thicker atmosphere due to the lower altitude, and thus light must pass through more water droplets and aerosols. Therefore, Mie scattering, like Rayleigh scattering, increases in effect. When red light strikes a region dense in water droplets or aerosols like a cloud or a fog, Mie scattering will radiate the red light, causing that same region to appear red. And this is responsible for the spectacular patterns of red across the sky we see often at sunsets.
So the next time when you're taking a nice sunset stroll along the beach, take a minute to stop and think, and appreciate the complexity of the beauty before your eyes. Even this simple explanation of sunset can be used to explain why the atmosphere is so important in preventing UV radiation, why night vision goggles utilize infrared light, and even why pollution makes sunsets even more beautiful. Sometimes you just need to stop and think.